on, I'd like to introduce our keynote speaker for Nanog 88. Shortly, please welcome to the stage our keynote speaker, Len Bosack, presenting From Data Links to Internets. Len co-founded a small networking company called Cisco Systems. Anybody ever heard of it? He made rapid progress in network speed and protocols. His current work at XKL is making the equipment for fast and reliable optical networks that are easy to deploy and operate. Welcome, Len.
Thank you, Aaron. Thank you, Aaron. Well, welcome to my tour of a very busy decade. This is the time where we went from barely being able to reliably communicate from computer to computer to being able to build something that you might recognize as an internet. So there's a lot of material here. It was a very busy decade, and I'm going to try and compress it into less than 45 minutes since we're running a little behind. I hope I've chosen an interesting selection of things. The intellectual framework is, in fact, the series of decisions and developments necessary to produce the thing that makes internets, which is a router. And the events matter because they had consequences. This is, in a fair part, how the network age was built. So, all right, there we go. Having fun with the technology. So, what I'm going to describe is, in effect, my fourth career. I've had a busy life, and I had a busy life after this, too. So I'm on career number 6, in case any of you are curious. So I was all of these things. I was a mathematician. I was engaged in symbolic computing in the 1960s. Then came building computers, both their hardware and their software, and then finally, what we're going to talk about, the networks. So, as a mathematician, my interests, without any ability to predict, turned out to be in what we today call discrete mathematics. You may recognize it as the underpinning of computer science. So, I mean, the algebraic rings are not everyone's favorite topic, and I don't go into them because people tend to glaze over a bit. But essentially, I learned about undecidability from the formal language approach to it. I learned about incompleteness from Alan Turing. The next phase was symbolic computing with languages that maybe one of which will be recognized, and that was those languages would include Trac, Lisp, Snowball 3, and Snowball 4. Not many people doing it at that time, turns out. Now, at the end of the 60s, it was not easy if you wanted a job in mathematics. So, okay, went into electrical engineering. If you're an engineer, you build stuff, and you can usually find people who want you to build stuff. So that was my simple-minded reasoning. At that time, this was the golden age of computer hardware design. And so that's where you go. Unfortunately, we weren't actually all that good at using them, so here came things like programming languages, operating systems. I guess that was the invention of computer science, eh? Very early on, about 1972, I had some access to ARPANET mail, and that must mean it was within months of its actual function. And it was real clear that over time, this was going to become important. So, I spent the 70s building computers and their operating systems, and finally got around in 1979 to head for the West Coast and another notch in the old Union card at Stanford Computer Science. August, September 79, I show up, and what was happening was the ARPANET was in the throes of being transformed into the first internet. Not only that, but there was a tremendous tumult, I suppose you could call it, about ideas for computer networks. Everything you can imagine, every topology. There were protocols already in existence that you would recognize as internet protocols. So, here we go. You want to build a network? Well, you better have a host. Actually, you better have more than one host. And what do the hosts need? Well, first they need network hardware. There just wasn't anybody building it at that time. You're going to need your drivers. You're going to need protocol implementations, both the part in the operating system and the user programs. And the ARPANET community was singularly well suited to do some of these tasks. The cooperation in terms of sharing ideas and the software that were built on top of the ideas and some of the hardware, unparalleled. No one had really made this much progress this fast. All with the, how do you say, obsolete ARPANET. Okay, well there it is. The ARPANET was a full-function non-internet. If you don't realize, it provided remote access, all these things, file transfer, mail, miscellaneous protocols, and it was perfectly good for rapid cooperation across time zones and across the country. I can't see people in this room easily imagining life without a network. Yet that's what most of the world experienced. And the ARPANET community was surprisingly small, hundreds of people really, in terms of doing these jobs. But in about 3 years, the ARPANET was moving what you recognize today as internet traffic. And while what people see as today's internet, the general public, it's still the internet. The bits and bobs that you actually make with your day jobs here, that's the internet. All the rest is really applications. So, want to build a network? All right, well, you better choose your network. Literally everything that you could imagine was available at that time, whether it was fiber, whether it was coax, different types of coax, different types of twisted pair. And people ran IP over everything. And it was a real-life torture test of whether this protocol would be network independent. Well, yeah, it worked out that way, as you remember. So, at Stanford, we chose Ethernet. Easily done. We had close ties with Park and the Alto 2s. We had 32 Alto 2s. They were running on the 3 megabit coaxial Ethernet, which was not without its troubles. It was a bit fiddly to learn how to put those taps in. It involved drilling a hole in the side of coax. There was a jig for it and all of that, so we learned how, and this turned out to be a good choice for us. Okay, we had a variety of hosts. The Altos weren't the only ones. They were the ones we had initially with the greatest number of network interfaces, but we had a collection of PDP-10 systems, and they needed better interfaces than other people were building. As you see, I call out a number of things that you need when the host is fast enough. You need to do back-to-back sending and receiving. You need efficient buffering with packet size. We were able to match hardware buffering with packet size distributions. And these really were the first, you'll hear me say the phrase interconnect grade interface, and I'll talk about that in a bit. And we had, there were 2 network interfaces associated with each instance, and you could have either 3 or 10 or 2 each, or 2 of any one. All right. Guess what? If you succeed and you start to connect computers to networks, the value of the next connection increases. And so more people want their computer connected to your network. And there started to be more demand than we actually expected. Now, this is a time where we barely had all the network hardware and things working very reliably. And so we could build analog repeaters that would almost double the physical length of the network. We could build digital repeaters, which gave us maybe a three-way split in terms of topology. But if we were going to go much further, it was quite clear that some sort of store and forward was going to be what was going on. Which brings us to early routers. Now, these started out as nothing more than oddly configured small computers. And when I say oddly configured, they had, of course, multiple network interfaces. And all of these things were used. The Honeywells were the IMPs, the PDP-11s, relatively new, but MIT had considerable success with some code running on PDP-11s. And we, of course, used the Sun components. Now, having faced problems with repeaters and being in a hurry, one of my fellow grad students at the time decided that he was going to take a Sun processor and 3 of the 3 megabit Ethernet cards, and he was going to write a program that was going to give us a switch. And it was a very well-conceived, well-crafted program. He managed to debug it in a reasonable period of time, and it did not go well. We had 2 hosts. This may have been the very first broadcast storm. I'm not actually sure about this, but it was certainly among the first switches. We had 2 hosts that could eventually get caught in an indefinite loop of sending error message broadcast to each other. But it didn't happen right away. The network ran reasonably, sometimes for hours on end. And it was a bit of a puzzle to debug. But, all right, we did figure it out. Okay, now let's digress for just a moment. Here we are, we've gotten to the point where we've built host interfaces, operating system support, user program support, and there were some people wondering, is this really anything but an academic exercise? Was this ever going to be practical? On the left is a graph that a number of you will have seen before. This is the ARPANET map as 81 was turning into 82. It's 50-ish IMPs, maximum degree 4, typically degree 3 or 4. The one on the right is, as you see, fairly recent KIDA description of the internet. In those 4 decades, how would you have known that the thing on the left would turn into the thing on the right? Well, I had a little bit of an answer. Being a mathematician, I couldn't help but model things. So, what were people worried or criticizing? There was just too much computation involved in this. This was never going to work in hardware. This just couldn't be done. It was too complicated. And there was way too much software involved. This is just impractical. And even worse, nobody really understands what happens when you build these networks. Okay, that's kind of sobering, isn't it? Because no one knew. We didn't. So here we go. Again, being a mathematician, I can't help but model things. By this time, I was using MATLAB as my desk calculator, so there's a lot of things I could do conveniently that might have been more difficult. So I experimented with various random graph models. My reasoning was, well, you know, if all it was like the phone company where people engineered everything, that would be great, but there'd only be 3 networks. And that wasn't going to be very interesting. So I assumed that we'd get sort of more or less random growth, organic growth. And after experimenting with a whole bunch of other things, an inverse exponential degree distribution seemed to give both networks that connected and kind of looked to me like something that might happen organically. I point out that the one on the right is Hard to imagine at that point, when I was looking at the one on the left, that it would actually turn into the thing on the right, which is a very good model of the mathematics that I used. Okay then, that told you some things if you believed it. Say, for example, if you wanted to build a network with 10,000 networks, you might need a router with as many as a degree 30 connection. Simple calculation. And those were numbers that were on my mind. And you'll see them recur later in the presentation. All right. So, it kept growing. We needed better routers, and several different attempts ensued. At Stanford, our first pass was just like the IMPs. We mapped our Net36 address onto a PUP address. Why PUP? PUP stands for Park Universal Packet, and it was sort of an internet protocol, but they had documented a reasonably well-conceived distance vector routing protocol. And so we did just what our colleagues at BB&N did and mapped the addresses. Worked surprisingly well. We added more actual explicit TCP/IP, and ultimately, people started asking for them. All right. We're a bunch of researchers. We don't know how to run a company. We don't know how to run a factory. We could do things in smallish quantities, and people wanted our interfaces. They wanted our routers. That's quite a stretch from the research mission. Now, at this time, ARPA was, or DARPA, I think the Defense D came around that time, was in Arlington, Virginia. And there are various funny stories about going to meetings at ARPA, but after one of them, I was talking to one of the program managers and sort of saying, what do we do about these things? People keep asking. We're not set up to do this. And his comment was, well, having our technology commercially available is actually an explicit goal of ARPA. Okay. He couldn't have been any more explicit. So you start thinking, what are you going to do? And we sort of in '84 and '85 started about to make a little networking company, and it was truly tiny. And I think you've heard of it, as they say by now. All right. Engaging in the task of better routers. Routers are not general purpose computers. They're really not much like each other. They use computer technology, but they just do different things. First off, they have this absurd need for robust interfaces. And when I say interconnect grade, I'll tell you in a moment. They're specialized computations. You do network address manipulation over and over, and you don't really do that much else. You need to do address lookups. And something that's not normally a factor for most computer systems, your bus bandwidth is right in your way. Okay. Let's talk about the interfaces, something that is a pain to this day. There's no question, if you don't stand line rate all the time, you're not really up to the job. Routers basically are fundamentally real-time systems, and that means never saying, wait for me. So everybody has to stand something. When one network has difficulty, and they do, the other networks and the router itself should just continue on. When that problem is cleared, it should pick right up. Particularly problematic are cases where a router thinks it has a live network interface and the packets are simply going off into space. This black hole problem, you see versions of it even today. It's especially a goal you should avoid, to avoid it. All right. So it's getting to be, must be late 85 at this point, and it was pretty clear that we needed to build something that was a higher degree component that had a pretty good switching capability. The answer was a thing we called the MCI, or multi-channel communications interface. It had two 10 megabit Ethernets, it had two 4 megabit HDLC serial ports, and it was basically a local memory-based router on a board. It was built around about a 100-bit, very long instruction word computer, and it was just barely general enough to switch and route all by itself. Although we couldn't do that at first. That took a good deal of development before it actually got to do that on a routine basis. Now, to a certain extent, this answered the question of, can't I have a bad one sooner? It was just what fit. We put everything on the board that we could fit, and we were praying that that was good enough. It was remarkably good enough, since without all those other ideas we had, I would have never, if they knew they were going to make 250,000 of them, I never would have let one of the engineers get away with some things I let him get away with. But, well, it was better than we thought. Okay. Now this runs on. We've been successfully selling these things for a while. The world is getting better. We discovered that one good trick was, there are a lot of protocols in the world at this time, so we would try and figure out how to reverse engineer a router function for almost any protocol. And that was essentially a software-only implementation at first. And if it caught on, we'd figure out how to accelerate it. Okay. In that same time, I was regularly a speaker at various technical and near-technical conferences, presenting essentially packet and internet technologies. I remember giving the same TCP talk, must have been 20 or 30 times. And it really was the nuts and bolts of TCP, because it was so alien to people. But by '87, it was real clear to me that these technologies were going to have a place in the world, a durable place in the world. So all going in the course of 4 years from, is this going to be useful at all, to, yeah, there's a place for this. Now, my talk, this was an ITU. ITU has a conference every 4 years. This one, I think, as usual, was in Geneva. It was in a warm autumn's day, I think it was. The air conditioning wasn't working particularly well. I was the last technical talk on the last day. Trust me, that meant that you really got the people who were interested. And as I was giving the summary, you look out over the room and you see people sort of shuffling a little bit because they knew I was coming to the punchline, or what they thought was the end. Gave the summary. I thought they were basically thinking about which of the beers that were available they were going to be enjoying, and it was about to be over. And so as an afterthought, I just summarized the whole thing, because the increasing efficiency we were attaining with the then somewhat new technology of packet switching led me to the conclusion you see on the screen, that voice would become a minor contaminant in the computer data stream, and no one would bother to separately charge for it. I might as well have set off a grenade. And it just seemed trivially obvious to me. I didn't know what I was doing, but they, of course, recognized where all their money came from. I have a story about a vice president at Bell offering the same advice many years earlier, but I won't tell that now. I point out, by the way, that by 1993, data revenue had exceeded that of voice, 5 years in advance of what I personally had believed at the time. All right, back to the main line here. So, having done the MCI, having seen how it was used, having seen that networks were growing pretty rapidly, the world was evolving. There were bigger networks being built, primarily now commercial networks. But still, the ARPANET had an outsized influence, which I'll talk about in a moment. So the C-bus system that we built, we called it C-bus for communications bus. We give you 5 interfaces targeting 100 megabits per. There was basically a memory switch card, and I figured we needed to be able to do 500 megabits and switch 1 million packets per second. With those cards that you see on the screen, that 6-port Ethernet, which was at the time considered quite a miracle, these cards had a total surface area of about 120 square inches. And we could get these Ethernets on there only by using the largest gate arrays available, 1 per interface. Xilinx should thank us. Although we were a pain to them at the time, it did advance their thinking about what's possible. FDDI was a 100 megabit fiber interface. It's probably an acronym that very few have heard of. And we had an 80 megabit serial interface, which was really used to drive 43 megabit DS3 lines at some of the supercomputer centers. But I point out that this could build a degree 30 router. And that was still on my mind. How big a network were we going to be able to build? All right. It was clear that we were succeeding at building IP networks. And the question still was, could we go, how large? Could we grow larger? Could we go faster? And the C-bus was my work in progress. And so, all right, I had other business in Los Angeles, but on the flight, it's a short flight from San Francisco Bay Area to LA. And I was going over some of our measurements done on a prototype, or breadboard, whatever, laboratory C-bus system. And it was clear that with a bit more work on the microcode, we could get to 1 million packets per second. And some years before, there weren't many people in the beginning. And so, Postel and I would wonder about, how far could this technology go? And so finally, it looked like we were going to be able to do it. This system would switch fast enough and have a large enough degree that we could cover effectively all the computers in existence. So I had the other business, and I basically diverted myself over to ISI. It's not exactly a big diversion. They were in the Marina Towers in Marina del Rey at the time, and maybe still there. But and I'm not someone who's prone to break into other people's meetings or anything of the sort, but this is sort of important enough for me that I did. I'm sure I pissed off various people in the process, but that's what I said when I came in. We'd had this discussion years before, and I'd actually done it. So, also still on our minds were, how do you make it keep growing? It's 1980, late 1988, late-ish 1988 or thereabouts, and the primary internet routing mechanism was a protocol called EGP, running over routers connected to the then somewhat straining ARPANET. And again, a few people here would remember this, but there was absolutely a flame war in progress about whether you wanted a distance vector or a link state routing algorithm. I see some people chuckling. There's still occasionally, I think, some debates on this. And mathematically, we just know what these algorithms do. They each have different costs and different advantages and different disadvantages. You can get good results with either of them. The other thing that was on my mind is essentially all the routing protocol proposals had some means of error compensation in them, because you just don't get everything, let's just face it. And what you were doing was basically redoing the work of TCP. Okay, with those thoughts in mind, why not get something to replace EGP that did not explicitly prescribe a route decision procedure? So there's that big hole in BGP, if you all remember, that it didn't tell you how to decide. Well, that was deliberate because I needed to get something done sooner rather than later. That is to say, get it done at all. And not reinvent TCP. So why not just use it? Okay. How do you spread this? So you see this, this is a famous napkin. I was standing there hovering over Kirk Lougheed and Jakob Rector in the cafeteria at the MCC in Austin, where an IEF meeting was proceeding without us. Well, it just took longer than lunch. And these two folks were technically capable, extremely intelligent people, and they were not understanding my urgent need, my apparent irrational urgency, and why it is that I picked those two organizations. IBM was intimately involved with the emerging NSFNet, perhaps the eventual sort of successor of the ARPANET in the research community. And Kirk, of course, worked for me at Cisco, who was we were starting to become probably the dominant router vendor. Okay, so here's a little more of the mood music. EGP Reaching is practical limits for various reasons. It was close to an N-squared protocol, and the updates were getting rather large. Probably not obvious, well, certainly not commonly known. The IMPs had a 1008 octet MTU. That meant things were starting to fragment, and trust me on this, many routers were not very good at reassembly. So this was starting to become a technical problem. And yes, those wars were really still going, and they went on for several years afterwards. And as a mathematician, that just appalled me because there's nothing to argue over. They're just two things that you could choose between, and a little hybridization here or there makes each of them stronger. And, well, you see the last 2 points, which I described the reasoning. So I eventually wouldn't let go of them until they had finished something. And it was 2 or maybe 3, I don't remember which, napkins later, but I understand you're suffering to this day from the decisions I made then. It has at least survived because it was intended to be an upgradable framework. That part we succeeded on. All right. So, when we were going through the C-bus design, it was intended to have a future. Everything about that system was designed to grow. We were right at a technological cusp in terms of our friends in the IC business, where we probably could take that bus from half a gigabit to about 2 gigabits per second. We were sure there were going to be more interface types. Although to my great surprise, gigabit Ethernet didn't show up for about another decade. And I know a lot of things about Ethernet and how it came and went, but that surprised me. We knew we could double the switching rate. That was, in part, the actual performance of the CBus1 controller was determined by some critical components that our friends in the semiconductor industry were promising they'd get better ones to us real soon now. Like every other technology promise, real soon is sometimes further than they think. And memory. Memory was a problem. Inconceivable to people nowadays that memory and its interface and bandwidth were still problems. And there were coming advances that we could take advantage of. But I also wanted to use a different memory organization, which would distribute the buffers out into the line cards. And there's a 24-bit memory address on the C-bus, and that would give you the imaginably large buffer space of 16 megabytes. And we could make it go a little larger by not referencing bytes, but that gives you a sense of scale. People don't even think of 16 megabytes as a memory nowadays. I'm not sure what they call it, but that was the sort of amount of memory that we could not get. But with that scheme, we would have been able to use faster and interfaces for a good long time. By the way, I point out, lest anyone imagine the head-of-line blocking problem does not occur in the scheme we had in mind, because the queues could deliver things out of order from the source interfaces. So the usual problem here is where you have a congested output interface, things congest back up at some input interfaces. Well, the congestion might be there, but you could compensate for that, but you weren't going to get head-of-line blocking. So the problem was understood far earlier than lots of folks wanted to admit. Finally, things that shouldn't be forgotten. Well, there are a lot of, I'll give you a little additional summary, but with regard to interconnect devices, your interface performance matters enormously. We sometimes see people selling interconnect systems today that just don't make it. The interfaces really aren't interconnect grade. And it's incredible to me that anyone would accept that. Now, a long time ago, very early on, and I didn't go into a lot of this because it would have taken too long and most people find the topic really boring, but the inter-arrival time distribution for network traffic is not like telephone traffic. I mean, I was an old Bell guy. I understood, you know, Poisson and Erlang, and that was relatively, that was settled art as far as I was concerned. The computer traffic, to our surprise, was not that way. It has what's called a fat tail or self-similar property, and you have to deal with buffer overflow. You can't just keep adding more or it just collapses from the indefinite delays that you provide. I think that many vendors went through that buffer bloat problem and perhaps they're doing better consistently now. And finally, no matter where you are in the network speed range, it still is all about the pins. We were limited, starting with the MCI, to how fast we could get data down a single package pin. And what's the singular problem at 800 gig? How much data you can get down a single package pin. It's still with us. It hasn't changed. The physics is different. I mean, now we're moving into hard millimeter wave physics, and that's going to be another learning experience. The last time the industry tried that was going from 2.5 to 10 gig, and that hurt. That took an extra 5 years. We'll see how much better we do now, but it's really all about the pins. And to go faster, it's really all about the pins. It's kind of a one-note song here. Now, okay, I've cut a bit into question time, but I've sped things up enough. One last sort of overview. There are so many people involved in all the work that I described. Andy Bechtolsheim and the Sun Components, you've heard Kirk and Jakob, and there are just, and so many of them, so to my personal regret, a good number of them are gone. They're no longer with us, but if I'd put them all in, I'd be on slide 4 right now. So something had to go, and I've given you one view of the flow of events through this time. It was a wild ride. And you all seem to be enjoying the result. Okay, with that in mind, I think it's time for questions. Anything remote?
No, I'm remote.
Okay, not so far. I don't know. Either I bored you or I stunned you. I'm not sure which it is.
Hey, can you explain what you meant by by the pins?
Oh, sure. Everything ultimately electrically goes down to a connection between an integrated circuit and the circuit board that carries it. And as you try and make those pins change electrical state more and more rapidly, different physical processes come into play. And in the sort of 100 megabit range, you get things with understandable with UHF electronics, capacitors, inductors, things of that sort. As you get into the past 2.5 gigabits, you start to deal with actual microwave physics where the dielectrics aren't dielectrics. The capacitors become lossy. Things start to matter in terms of just a few extra centimeters of transmission line now mean something else. And as you go into above about 30 gigahertz, well, this is the nightmare world for a pure analog engineer because everything's a lossy resonator connected by a radiating transmission line. I see some people with electrical engineering backgrounds are chuckling. Yes, indeed, it's happened. It's come to pass. And it gets harder and harder. And you can go shorter and shorter distances. So it's still with us. Now, when I was at Bell, we used to kid each other that in the future, computers would be about the size of a golf ball. They would glow red, and they'd be connected with a bristle of 1 millimeter waveguides. And then, of course, we'd console each other saying, well, yeah, we're not going to be around. That's not going to happen. You know, that's going to be somebody else's problem. Well, it's my problem now. Oh, well. Another question.
Hello. My name is Rosie Schechter. I'm with Amateur Radio Digital Communications. And I'm curious just how many napkins you have with sketches on them, and have you saved them?
Oh, I don't know. I must have had 20 or so over the years. And no, those got saved only by accident. That was, I suppose, happy accident because it lets you see how. But by the way, those of you who are familiar with BGP will recognize what's on that napkin. That's not alien territory. It is how it started. And a few of them went by. Many of them were much messier than that and got transferred into some other form. But no, I don't have many more napkins of that sort. But it's a good story, and I thought you should be amused. Okay.
Hi, Len. Thank you again for the presentation. David Swafford here. When you left Stanford to go create Cisco, how did you balance the intellectual curiosity versus the need to build a product?
When you have to meet payroll, it focuses the mind. I mean, I can't give you a simpler answer.
Okay. Thank you.
I mean, it's almost that simple. Yes, sir.
Thanks again. Steve Wallace from Internet 2. I remember installing the gear that you described. And one of the things that I remember early on was one of the reasons we were installing Cisco gear was because it supported multiple protocols and bridged those that didn't. Mm-hmm. And I kind of am curious about when did you realize that the future was only IP and that that was really the direction to focus on?
It faded, these other protocols faded away very slowly, actually, because when people put in a system that solves a problem for them, they're not motivated to throw it away just because something new has come out. So we attempted to give them a soft transition, which is the best way you can have a revolution. It's not apparent when it's happening. And that was part of the secret. I mean, Vint figured that out from his perch in DC, that it had better not be too hard a revolution or you just get crushed. So that IP eventually took over wasn't a goal necessarily. It was a fact that was accomplished because it became the most useful protocol. That we could deal with all these other protocols let us get along with other choices made years ago. And that had a commercial utility because you weren't at war with people who got good results with their old equipment. They could still come along with you. And ultimately, in time, IP did take over because it was just more useful. It was more universal. And that's the answer that I can give. Yes, sir.
Question. Can you go to Remote question, Len. So if you could go back and change one decision you made across your design process over the years, what would that have been?
Oh dear. There were so many. So many of them were wrong. Okay. All right, I've got a few minutes. Right and wrong decision making. If you make a lot of decisions, you're going to make a lot of mistakes. It's just true. And what you have to be, to succeed under those circumstances, you have to be willing to figure out which ones were a mistake and which ones you need to change promptly. And so I tried very hard to keep track of things that could still be changed. So many things. Once you go far enough, it's just a mistake you have to live with and you have to compensate for the next time round. But anyone who's building something new has to expect mistakes, and you have to expect that you will adapt to them and change as fast as you can once you're sure it's wrong. Because there were, as I say, I can think of half a dozen things that, the good news is at least half a dozen things that went some distance and have never seen the light of day, and they didn't deserve to. So I can also think of a few things that got out that I wish I hadn't let out, but we'll leave those alone. So to try and single out a single thing that I wish I could change, well, it's not a mistake and it's not something I have any control over, but I wish John had lived another 10 years. So that's not my mistake. It's not mine to correct. But that's a sincere wish. All right, we've come to the end, about on time. Thank you all.